additional option that we can use with indirect memory operands is also adding address displacements. So for instance, consider this type of array. So we're just going to add this example to an array of essentially an array of 100 zeros to name table to our data segment, and this is an equivalent of declaring an array of words which are 16-bit integers. So an equivalent in C would be short, right? So short is a keyword in C programming language, and we're going to create an array named table of 100 elements, and we're going to initialize everything with a 0. Okay, so you know that the first element in this array is going to be initialized with 0, and since this initializer is shorter than 100 elements, the rule in C is that the C compiler will generate an initializer code which will set every single one of these 16-bit size integers to 0. Okay, so we have a definition of our table right here. So let's keep this in view in our data segment, and let's try to experiment a little bit. And back to the topic of the address displacement, let's use this example in our code. So this is yet another continued the conversation about various types of operand addressing. So here, of course, AX is a 16-bit portion, the lower 16-bit portion of register EAX, and we're just going to refer to the table, which is our symbol inside the data. And let's set register ESI, for example, ESI. We can say move ESI, whatever, just a certain value. Let's just use value 2. Okay, so this is just an index right here. In fact, basically what is happening here is that we use our table. And by the way, for technical reasons, so let's just use 0 at the beginning. Okay, and then so this is our table. Of course, ESI is just 0. So how this gets resolved is basically the table, which is the offset in our data segment, is added to ESI, which is 0. So this is what we call address displacement. So essentially, we're adding constant value to the address expression, because this is square brackets, which of course always refers to something in memory. So this is called a direct memory specifier, like this. Very common type of displacement expression. Okay, we could so let's build this just to make sure that all of our syntax is correct. Okay, so it works fine. And of course, this is 16-bit because we decided to use word as an example of a 16-bit integer. And other possibilities, so this is an equivalent to just saying ESI plus table. Okay, you can write it like this. Okay, so it's the same thing. Or you can write it like this. We can try this as well. Maybe table plus ESI, just to verify that all these variations would be processed by our assembler. Okay, so everything works. So this is just the notation which would be familiar to a C programmer, because this is how array name looks like in C, and this is how array index looks like in C. So altogether, this is essentially an idea is that we're trying to get, retrieve one of these integers, 16-bit size integers from this table of integers, and load it into register AX. But the same thing can be written like this and like this. It's all the same. It's a very simple idea. So this is the displacement and this is the address. And funny enough, our address here is 0. Okay, and so displacement is actually giving us something real in this example. Now also remember that table ESI altogether, the effective address, the final effective address, will be different every time we run the program, because the loader may decide to place our entire global data segment in a different space, at a different address. So this is why address expression table combined with ESI is actually a relocatable expression. So if we turn on listing building, this will be marked as relocatable expression, address expression in a listing file. All right, so yeah, and so this is what the idea of the displacement is. Displacement is like an offset. Okay. Now there's a possibility of multiple displacements, and these multiple displacements would involve multiple displacements like this, table plus 6. So let's try something like this. But I think this example was taken from real mode, 16-bit real mode examples, so I'll just have to slightly modify this. In fact, so this is, we'll say indirect operand with address displacement. Okay. And these are also same thing. It's just all these syntax, all these 3 move instructions will generate exactly the same instruction. Okay, so the next thing here is that we can try to combine these notation using multiple displacements. So let's try this, and just copy and paste, and I'll just update that. Let's try EBX and EDI plus 6, just like written over here, and let's just let's move into EBX as well some sort of value. Let's say move EBX. For now I'll just use 0, okay, just to be able to test this syntax. So this certainly looks like a multi-dimensional array using 2 of these registers, one displacement and also another displacement. So let's give it a try. Okay, so this works fine. You can see the 2-dimensional array can be written with 2 different indices using, in our case, EBX and EDI as 2 indices into table, which is, in our case, a table of 16-bit integers. That they all look like short integers in the C program, and we also combine it with another type of another type of displacement, basically combining this with this. So all of this, what it all means is that, so these are examples of multiple address displacements right here, just to know that it's all possible. So the idea behind it is that it's all the same as, in fact, let's just write this again. So one more time. So the idea is that all of this notation is just a convenience notation for, let's try this. If we just use one set of square brackets and just use something like this. Let's see if assembler will be able to take this format to because that's the idea of combining all displacements and all these things together. Okay, so this works the same way. Let's just set a breakpoint here and quickly debug. Just basically debug, start debugging, and just real quick take a look at the disassembler. And you can see that when I switch to disassembly view right here, you see that both of these instructions, although they're written in a different form, they just the disassembler actually picks this form when it's trying to show us what is going on, and it's just simply that the assembler itself at the time when it assembles the source file, it combines table with 6. So that's why we see all of this. And of course, we're never seeing this number in our program, but that's where the table was relocated to. So this is the relocatable address. And of course, this address is combined with EDX and EDI. So anyway, it's just, again, it's just a syntactical variation of indirect operands with address displacements, but also using multiple displacements like this and like this.